Throughout this video, I will be explaining the physics behind guitars. A little more specifically, I will be exploring the principles of physics which allow both acoustic and electric guitars to produce sound. Most basically, guitars produce sound through amplification of the sound waves produced by strings after they've been plucked or strummed. The way that sound is amplified is the biggest difference between electric and acoustic guitars. In both cases, these strings act as a vibrating object, but they disturb different mediums. In an acoustic guitar, sound is created as the strings vibrate the air surrounding them. However, the surface area of the strings are pretty small. The guitar's body allows more air to be disturbed because the strings force the body as well to vibrate at the same frequency, thus increasing the surface area of vibrating material, producing a louder sound. Strings alone do not produce a loud sound, as you can see with an unplugged guitar. So the increased surface area and open design of an acoustic guitar is important. Inside acoustic guitars, struts are placed for support and to channel the waves, forming a resonance pattern. Guitar builders or luthiers have experimented with different designs to create a more optimal sound. Since we know that the strings are passing vibrational energy into the physical body of the guitar, and we know that different mediums of different densities interact differently with these waves, our choice of building material is pretty important.
Because different woods carry sound waves differently based on their densities, they end up producing different sounds. For example, my acoustic guitar is made mostly of mahogany, which is a dense wood which is supposed to, for example, have a warm tone. Maple, on the other hand, which is an even denser and harder wood, is the wood which is used for the neck of my electric guitar and is supposed to produce a brighter sound, which can play a role in choosing which guitar you'd like to play. As for why we choose wood for guitars in general, woods usually have a density of 0.27 to 0.7 grams per cube centimeter, whereas a metal like lead has a density of 11.34 grams per cube centimeter. Since it takes more energy for sound waves to travel through denser objects, wood is an optimal material when we also consider its structural and aesthetic qualities as well. Because the sound we hear from an acoustic guitar is primarily produced by the vibrations of the wood, the overall sound is largely influenced by which wood species and shape we choose. However, this isn't really the case for electric guitars because their sound is primarily produced by electromagnetism. An electric guitar has pickups which, through magnetic induction, send an electrical current from the pickups to the cable into the amplifier, which then amplifies those electrical signals into sound. The strings, which are composed of ferromagnetic substances, oscillate over the pickup. The pickups have magnets placed under each string. The magnets are surrounded by a coil of copper wire, which makes the pickup an electromagnet. The magnets, as with all magnets, produce a north and a south pole. When the string oscillates over this magnetic field, it produces a change in its flux. Michael Faraday established Faraday's law of induction, a law which describes the production of a magnetic field from an electric current and how a changing magnetic field creates an electric current. We can imagine that the magnetic pickups have lines of magnetic flux. When the string oscillates over them, according to Faraday's law of induction, since the magnetic field is changed, an electric current is produced within the wires surrounding the magnets. This current is what is sent to the amplifier, which ultimately produces the electric guitar's sound. Having discussed the physics which go into producing sound in an acoustic and electric guitar, I was curious to discover if physics played a role in determining what sounds good and what doesn't. For example, here's two chords. One clearly sounds better than the other, and Josh McDermott, a researcher at the University of Minnesota, conducted an experiment to figure out why. Their findings were that musical chords sounded good when the notes being played produced harmonically related frequencies, meaning they shared a relationship, like their hertz being multiples of 100, and bad when the frequencies were not related. Harmonic frequencies are all multiples of one fundamental frequency, and this study suggests that this plays a role in how we determine what sounds sound good together.